Hi, this is Bob Rasooli from Orange County, California, and in today's session, I'm going to review with you one of the most challenging exam questions you will ever see from API 571, specifically from the topic of wet H₂S damage, blistering, HIC, SOHIC, and SSC. This question is designed to push your understanding far beyond simple memorization and into the real-world diagnostic reasoning that the API exams truly expect. Here is the question. During inspection of a carbon steel fractionator overhead drum operating in a sour water-rich environment with confirmed cyanide contamination, UT straight beam readings show several deep pit-like indications in the mid-thickness region of a shell course. No visible bulging is observed on the ID or OD surfaces. Subsequent wet fluorescent magnetic particle testing WFMT reveals no surface breaking cracks in the same locations. Which of the following best identifies the damage mechanism and explains why the UT signal appears as deep pits? Option A, hydrogen blistering. Internal hydrogen gas accumulation creates mid-wall bulges that can be detected as pit-like ultrasonic reflections even without visible surface deformation. Option B, hydrogen-induced cracking, also known as HIC. Internal laminations created by trapped hydrogen gas reflect ultrasonic signals as sharp, deep indications even when surface cracks are absent. Option C, stress-oriented hydrogen-induced cracking, SOHIC. Stepwise crack arrays oriented along residual stresses near welds produce multiple internal UT reflections even far from welds. Option D, sulfide stress cracking or SSC. Hard microstructures at the shell mid-wall create subsurface cracks detectable by UT even without surface indications. Let's walk through each option in sequence and evaluate which one is correct. Starting with option A, hydrogen blistering. At first, this may seem somewhat reasonable because hydrogen blistering does involve gas pockets forming inside the steel. However, API 571 clearly explains that hydrogen blistering produces visible bulges, usually on the inside diameter surface of a pressure vessel. These bulges are physical deformations that can be seen or felt, and they're considered a hallmark of blistering damage. In the scenario we're given, there is no visible bulging on either the inside or outside surfaces. Instead, the ultrasonic signal shows internal pit-like reflections. Blistering simply does not match this appearance. For this reason, option A is not correct. Now let's move to option B, hydrogen-induced cracking or HIC. This is the correct answer. API 571 states that HIC creates internal planar separations inside the steel. These internal cracks or laminations can make ultrasonic thickness readings appear as sharp, deep, well-defined pits, even though no actual pit exists. The UT wave simply reflects off that internal separation. This perfectly matches the description in the question. Also, cyanides dramatically increase the severity of HIC and the equipment mentioned. A fractionator overhead drum in sour water service is one of the classic locations where HIC is found. The fact that wet fluorescent magnetic particle testing WFMT revealed no surface breaking cracks also aligns with HIC because HIC is typically internal and mid-wall, not surface connected. Everything lines up cleanly, and that's why option B is the correct mechanism for this scenario. Now let's consider option C, which is stress-oriented hydrogen-induced cracking, or SOHIC. This tends to occur near welds, forming stepwise ladder-like crack arrays driven by residual stresses. The question describes internal indications in the middle of a shell course with no mention of weld proximity. There are no surface breaking cracks and nothing resembling a stepwise pattern. These features simply do not match SOHIC behavior, so option C is not correct. Lastly, let's look at option D, sulfide stress cracking, or SSC. This requires a combination of high hardness, high tensile stress, and exposure to a sour environment. It is commonly found in hard welds, heat-affected zones, or high-strength components. In this scenario, the indications are in the mid-thickness of a shell plate, not in a weld or hard zone. SSC generally produces cracks that can be detected by surface methods like magnetic particle testing when they are surface breaking. Since wet fluorescent magnetic particle testing, WFMT, showed no indications at all, SSC is ruled out. Therefore, option D is also not correct. In conclusion, the only option that matches every detail of the scenario is option B, hydrogen-induced cracking. This mechanism explains the internal mid-wall separations, the ultrasonic pit-like reflections, the lack of visible bulging, the absence of surface cracks, and the influence of cyanides in sour water service.